Welcome back to the Deep Dive. We're the place that takes dense research and, well, makes it make sense for you. Today, we are diving into computational geomechanics. Sounds heavy, I know, but stick with us. It's about a really clever numerical trick with huge implications for big engineering projects. Our main source is a 2015 paper from Computers and Geotechnics. Authors are Cecílio, Devloo, and a few others. And interestingly, they're linked with Unicamp Shore, but also Petrobras.
Yeah, that Petrobras connection is key.
Hmm.
It signals this isn't just, academic noodling. This is math built to tackle very real, very expensive problems in the ground. And our job today is really to unpack how they did it. They call it a simplified methodology for elastoplastic calculations.
Right. So taking the tricky part of modeling materials like rock or soil, that point where they deform permanently, and making the math faster, cleaner, and importantly, more stable.
Exactly. Stability is huge here.
Because we're talking about things like oil reservoirs miles down or
Yeah.
foundations for bridges, right?
Mm.
Why is modeling these granular materials, soil, sand, rock, such a computational headache?
It really starts with the physics itself. These materials are quirky. They're not like steel. Their strength changes based on the pressure they're under. They show this complex plasticity, very dependent on hydrostatic pressure. And crucially, they react differently if you squeeze them versus, say, pull them apart in different ways. Triaxial compression versus tension.
Okay, so simple models like basic elasticity
Mm-hmm.
just won't cut it if you want accuracy. You need these more advanced constitutive models.
You absolutely do. And those models are where the computational challenge really bites. They're typically built on three pillars, you could say. First, a yield criterion. That's the line in the sand, mathematically speaking, between bouncing back elastically and starting to deform plastically permanently.
Okay, the point of no return.
Sort of, yeah. Then second, you need a flow rule. This tells you how it deforms plastically the direction, the amount.
Got it.
And third, there's a hardening law. This describes how that yield boundary, that line in the sand, actually moves or changes as the material gets worked over.
And I guess when you mix those three together, yield, flow, hardening, they all depend on each other.
Precisely. It creates what engineers call a stiff, nonlinear system. Everything's coupled.
Which means computationally unstable.
It can be, yeah.
Yeah.
Very sensitive. A tiny change, a tiny misstep in the calculation, and the whole thing can just diverge. You need really robust integration methods.
Okay, so that's the problem setup. Complex physics leading to tricky math. What's the standard way engineers usually handle this plastic part in simulations? You mentioned a two-step process.
That's right. The classic method is often called the return mapping algorithm. It's iterative within each time step of a simulation.
The elastic trial. The computer basically hopes for the best, assumes everything's still elastic, and calculates a trial stress based on the deformation.
Kind of optimistic.
Huh, yeah, a bit. Then step two kicks in if that trial stress is actually outside the allowed elastic zone defined by the yield criterion. The material should have yielded, so the computer has to perform the plastic corrector step. It mathematically forces that calculated stress back onto the yield surface boundary. That's the return mapping part.
And reading the paper, it sounds like that corrector step is where all the trouble starts. The instability, the complexity. Why is that projection so hard?
Well, you're solving for several unknowns at once, and they're all tangled up in that stiff, nonlinear way we talked about. How quickly, or even if, the computer finds the right answer. The convergence really depends on your starting guess and even the coordinate system you're working in. Small errors like floating point variations can just stop it from converging at all.
So the physics is right, but the calculation method itself is fragile. Okay, this leads us nicely to the breakthrough in the paper. They didn't just try a better solver, they changed the view.
Exactly. It's a really elegant geometric idea. They start in the standard stress space, the Hay-Westergaard or HW space, which uses principal stresses. It's intuitive physically, but computationally, it can be prone to these convergence issues.
Okay.
Their move was to apply a specific mathematical rotation. They shift the whole problem into a different coordinate system they call the rotated Hay-Westergaard space, or RHW space.
And that rotation, that change of coordinates, what does that actually do to the difficult plastic corrector step? This is the really cool part, right?
This is the cool part, because in this new RHW space, that messy iterative correction step suddenly becomes geometrically simple. It transforms into a problem of finding the closest point.
Closest point.
Yeah, you have your elastic trial stress, which is outside the yield surface in this RHW space. The plastic correction is now equivalent to finding the point on the yield surface that is geometrically closest to that trial stress.
So instead of solving a system of equations, you're just finding the shortest distance.
Essentially, yes. They show mathematically that the direction that minimizes the distance, specifically the square of the distance, between the trial stress and the surface, well, that direction is exactly the same as the direction the plastic deformation needs to go in.
That sounds simpler. But why is finding the closest point so much more stable? Is it really that much better than solving the original system?
Oh, it's significantly more robust. Think about it like this. Solving the original nonlinear system is like trying to balance, I don't know, several spinning plates at once. Very tricky.
Right.
Finding the closest point, especially in the way this RHW space is set up, often turns the problem into something mathematically convex. That means there's usually just one unique minimum distance, one closest point. So the algorithm isn't balancing on a knife edge anymore. It's just rolling downhill towards that single correct answer. It's inherently more stable.
Okay, that makes sense. Stability is great. But what about speed? For these huge simulations, speed matters too. What was the computational game?
That's where it gets really impressive from an engineering standpoint. The original problem, the general elastoplastic step, involves solving for 7 variables, all coupled together. 7 equations, 7 unknowns, every single step. That's a lot of work for the computer.
7 variables, wow. Okay, how does the RHW closest point method cut that down?
Massively. Because of the geometry in the RHW space, the problem reduces to solving a nonlinear system with, wait for it, at most 3 equations.
3, down from 7.
Yep. Typically 2 parameters to locate the point on the yield surface in RHW coordinates, and 1 more equation for the internal variable that tracks material hardening.
That alone is a huge reduction. Less work per step means faster simulations overall.
And it can get even better. If the material you're modeling is perfectly plastic, meaning it doesn't harden, then it simplifies further to just 2 equations.
Okay, 2 is amazing. But I think I saw something even more dramatic in the paper for certain common models, like down to just 1.
You did. For some really common, really useful yield criteria. Think more Coulomb for soils, or von Mises for metals. Though it applies here too, the geometry in RHW space is so clean that the closest point projection can actually be found analytically.
Meaning, no iterative solving needed for that part.
Almost. You basically get a direct formula, maybe with 1 unknown left. So for those specific but very important cases, the entire return mapping algorithm boils down to solving just a single nonlinear equation.
Okay, that is incredible. From 7 coupled equations down to 1, you can see how that would radically speed things up. Simulations taking days might now take hours or less.
Exactly. And that speed up isn't just convenient. It allows engineers to actually use more realistic, complex models that they might have avoided before because they were just too slow to compute. Right? They don't have to sacrifice accuracy for computational feasibility. Okay, let's ground this. They tested this method on a specific realistic model, the generalized Sandler-DiMaggio model. Why that one? It's a workhorse model, especially geotechnical and petroleum engineering. Originally for soils, but Petrobras and others use it extensively for rocks deep underground, under high pressure. It captures key behaviors really well.
And the generalized part, what does that add?
The generalization is important. It brings in the effect of the intermediate principal stress mathematically through something called the load angle.
Load angle. Sounds technical. Why does it matter for realism?
It matters because real rocks and soils often behave differently depending on the full 3D stress state. It's not just about maximum compression. The generalized model uses this load angle dependence to capture that difference, making it more accurate for complex loading paths, like around a well bore.
Got it. So, a realistic, widely used, somewhat complex model. Perfect test case. What did its yield surface look like in their new RHW space?
It became quite neat, actually. In the RHW space, the yield surface lines up nicely with one of the axes and splits clearly into 2 parts. There's a failure function, often denoted F1, and a curved cap elliptical function, F2.
Failure and cap.
Yeah, roughly. The failure function governs the shear strength limit, while the cap function handles the behavior under compression, like how the material compacts and hardens as pores close.
Okay. And they ran a standard test simulation, right? Uniaxial loading and unloading using parameters for a specific sand. What did that show?
It showed the algorithm working beautifully. In the simulation, during the compression phase, the stress state correctly projected onto that cap function, F2. It modeled the compaction and hardening just right.
And unloading.
Then, as they simulated unloading, the stress path moved across and correctly projected back onto the failure function, F1. The algorithm handled the transition between these 2 distinct parts of the yield surface smoothly and critically efficiently.
And the numbers. How efficient was it? Did it converge quickly?
amazingly quickly.
Yeah.
The paper reports that for this quite complex Sandler-DiMaggio model, using their RHW minimization approach, the iterative solver needed less than 5 iterations to converge at each load step.
Less than 5 iterations. That's really fast for this kind of problem.
It absolutely is. It confirms the stability and the speed gain they were aiming for with the whole RHW transformation.
So let's wrap this up for everyone listening. This deep dive took us into some pretty specific numerical methods, but the takeaway is, I think, quite profound. Sometimes the biggest leaps in computational power don't come from faster chips, but from a smarter mathematical perspective.
That's exactly it. By finding the right way to look at the problem rotating the coordinates into this RHW space, they turned a complex 7-variable system prone to instability into effectively a much simpler 3-variable or fewer system that's robust and fast.
And that robustness, that stability, is paramount when you're simulating things where failure has massive consequences. It lets engineers trust the results of complex, realistic models.
Right. They can use the physics they know is right without being limited by fragile computation.
So the final thought here is maybe about the power of abstraction. It seems like finding this clever geometric view, this closest point idea in a rotated space, did more for practical computation speed and reliability in this case than just throwing more brute force computing at it.
It really highlights that connection, doesn't it, between, seemingly abstract mathematical structures and very concrete engineering outcomes. A smart geometric insight leading directly to faster, safer designs based on better simulations.